This is the last section we need to do in chapter 5.
How many more chapters we need to get?
Let's get through it.
20, what?
Great way to start.
What?
Yeah.
25th?
Right, I'm just gonna cut to the chase here. Theory's a bit dense. Mostly, the main contributor here is usually Frobenius and guys like that, but it sort of gets weird when you're dealing with singular points. We're just gonna sort of jump into it. First, we look at equations with so-called associated Euler equations. Particularly okay, so remember what Euler equations are, right?
That's up.
Yes, I'm going to make that more precise about what I mean. Remember,
Messed up.
an Euler equation has the form. What's the form of an Euler equation?
R times R
Alpha.
minus 1.
Alpha x squared y double prime plus beta x y prime plus gamma y equals 0. Right. So when I say the alpha and the beta and the gamma terms, I'm talking about this guy here and this guy here. So remember, the idea was these guys sort of look like quadratics, right? You have an x squared, you have an x, you have a constant, right? Whenever one of these guys mess up so you don't have a quadratic anymore, you don't have that form, you say it has an associated Euler equation. It's not technically an Euler equation, but we can sort of start to match it with an Euler equation. So for example, this example. If I say x squared y double prime plus x squared y prime plus 3y equals 0. Notice that here, the beta term falls out of line, right? It doesn't look like x squared x and a constant anymore. This guy's an x squared, right? So you see here, the beta messed up. It's a little bit messed up. Have you guys seen that YouTube video?
Yeah, it's
Never
much
mind.
purple.
What?
Much purple.
Thank you.
The guy was green. Never mind. I
I
should just say it anyway because my friends would crack up if
You
they
need
watched.
purple?
Anyway. So the beta messed
3 pounds
up.
back for purple.
It has x squared instead of x, right? Now that's a problem. So basically, we obtain the indicial equation by ignoring the part that messes up. Okay, and by ignoring some parts, we get what's called the associated Euler equation. So here, associated Euler equation is basically alpha is fine, has the right form, you write it down. Beta messed up, just skip it. So we only care about the guys who maintain the form, right? Any guy that messed up, forget it. Only as far as obtaining the indicial equation is concerned, right? You just ignore it for a certain part. So this means your indicial equation here is r minus 1 plus 3 equals 8. Yes?
Question. So, what if like beta and the other one, like,
Everyone who messes up, you ignore them.
so it's just that one part then?
Yeah, so you just have the r minus 1. You'll always want to assume that the first part, well, at least in this section, the first part is okay. You can always write this as an x squared times something. I'll give you some more examples of that soon. So here, by omitting the beta term. So we're going to see we're going to do some more examples of this so you sort of get the idea. I'm going to give you a bunch of almost Euler equations. I'm just going to try to see, can you identify the indicial value? A here, we have x squared, y prime plus x prime plus. Here we have a bunch of almost Euler equations. They are very close to being Euler, but they're not exactly Euler because someone messed up in their form.
Do you have to multiply?
Start with this one. What's the indicial equation?
R times R minus 1
Plus r
plus
minus
R minus 1 by 9.
Right. So here, x squared, okay. X, okay. When you look at this term, not okay. This should be a constant. There's an x squared. What do? Ignore the x squared part.
Yeah.
So then this becomes r minus 1 plus r minus 1 over 9 equals 0.
Okay. Don't pretend that it's easy.
It's easy if you remember the form that the indicial equation has the form alpha r minus 1
I stand corrected.
r
Yes, it is.
plus gamma equals 0. So you're just picking out what the constants are, and if anyone messes up, you just drop them out. What about this one?
All of them.
The should have been 2x squared, but you have 2x on the y prime, and there's also
Yeah.
y. Should have been a constant, so the indicial equation should be r equals 0.
Yep.
Oh, yeah.
Multiply by x. Say, technically here, every single person messes up. It's like, you don't have an equation. You can actually get around that. Multiply by x.
That's so cheap, man.
Now what would the initial equation be?
Oh, this is everyone.
See, this guy is okay, this guy is okay, this guy messes up. So it's just 2r, r minus 1 plus r equals 0. You leave off the constant term because there's no constant term. What about this one?
Multiply by x.
What's the initial equation?
4 times r minus 1.
That's the initial equation here, that's the initial equation here. This one?
Same thing.
Multiply by x, get x squared y double prime plus x minus x squared y prime plus x squared plus 3x y equals 0. The initial equation is
4 times r minus 1 plus r.
right. This guy's okay. He messes up. All of this messes up. You just ignore them. That's your initial equation. Here.
4 times r minus 1 plus 3. Plus 3.
Plus
No.
1r.
Hmm?
Minus 3r.
Minus 3r
Plus 3.
plus 3. Right? He messed up, so you got rid of him. You multiply this guy out, you get minus 3x. So that fits the form, you throw him in. Here, the x messes up, you ignore him, but the 3 is a constant. That is okay, so you throw him. Right? Ignore the guys who mess up, put all the other guys. Okay, that's basically the idea. Okay, so. To solve these guys, we'll use series because the old method of solving Euler equations doesn't work on such equations. What was the old method of solving Euler equations? How do we solve it? If everything was fit the form nicely, it looks like a quadratic and all that, what did we do? C1 what? First, you get the initial equation, you find the roots, and based on whether it's 2 real roots or 1 real root or complex roots, you have the form, right? Basically, y equals x to the r was the form we assumed, right? Because it made these terms self-similar. Okay, so now when these things mess up like that, that method doesn't work anymore. So now we have to find something new to work, and we're in the series section, we're going to use series. Basically, we do something that we've done several times before. We take our cue from reduction of order. Assume the solution has the form y equals x to the r times some v of x, where v of x is analytic, i.e. has a power series expansion. So this means our y should be equal to x to the r times some power series. Which we can write here as n equals 0 to infinity of a n x to the n plus r. Right? So whenever you're faced with an almost Euler equation, to do the series solution, this is the formula, assume the solution takes on. Similar to a power series, but now it has this n plus r. We're sort of shifting the powers because of that single quantity. And it turns out with that technique, we can actually find solutions to these guys. It's a little bit different from the series solutions we've done before, and I'm going to show you how. Let's see. But finding the indicial equation is going to help us. So let's do an example. Start out with a very nice one. I think we already did find the indicial equation. We're going to see what this means later, finding the solution corresponding to the larger root. So let's see, how do you begin? What's the indicial equation? Multiply by x. This means the indicial equation is r times r minus 1 equals 0. This means r equals 0, r equals 1. This is the larger root. So we're going to find a series solution that goes with this root. Now remember, it's a second order differential equation. We expect two linearly independent solutions. It turns out one solution will go with this root, another solution will go with that root. And we just want the one for the larger root. So if you're paying attention, you already spot what's some of the changes that might occur. Remember, usually when we're doing series solution, we had the solution corresponding to A0 and the solution corresponding to A1. Well, that won't happen anymore, because if I get an A0 and an A1 here, and an A0 and an A1 here, that will give me 4 solutions. It turns out that either the A0 or the A1 will cancel. The A1 will kill itself, and just the A0 solution will be given here, and then the same thing will happen here. That's sort of the difference. Another difference is how our derivatives look. So, but other than that, it's pretty much the same thing. But this guy is also important, so make sure you pay attention to this guy. If you do everything correctly, you should see him pop up in your solution somewhere. So you should pay attention. It'll help you check your work. So. First major difference. Notice, index does not change.
Minus 1?
Yes, r minus 1. I just took the derivative. Why doesn't the index change? Well, now, if I plug in n equals 0, I don't get 0, right? My term will actually change. If I put n equals 1 here, I actually would get a different thing from the series, because if my r is not 0, then it won't work. Right? So the thing here is when you take derivatives, the index doesn't change. That's one of the major differences. This is n plus r minus 1, the n plus r minus 2. And now we plug those into our differential equation. Now, usually I prefer plugging it into the one that we get after we fix the problem. Because if you plug it in here, you'll get a to the negative subscripts, and it confuses people sometimes. I don't like doing that. You might get it here too, but there's less of a chance. So let's plug it into this one. This gives us
Exceed n plus o.
plug it into the ODE to get. I'm going to multiply x squared by this guy, which means this minus 2 will disappear. Plus, I'm going to take x times this guy, the y. So this is going to be infinity to n x to the n plus r plus 1. Okay, now what do we do?
Make the powers equal.
Make the powers the same, right? So we assumed our general form has the power n plus r, so it'll be a good thing to get all powers to n plus r. This guy's okay, means we have to fix this guy. How do we fix it?
Minus n plus r minus 1. N minus 1.
Okay, so what does this series change to?
N equal 1.
Starts from 1 to infinity,
And a to the n plus 1.
and minus 1.
N minus 1.
I need a minus 1 to go plus 1. X to the n plus r. Now, let's do the method where we evaluate some of the terms to catch these guys up. Because like I said, you should notice that if I switch this guy back to 0, it won't, I can't do that, right? It actually will make a difference. So it means that I need to get this guy to catch up to this guy. So I can evaluate one term from here, right? So when n equals 0, what do I get? Plug in n equals 0 here, what do I have?
R plus r times r minus 1. A to the 0.
A to the 0,
X to the
x to the r, plus
the
it's
series.
the big series starting from 1 to infinity of n plus r minus 1, an plus an minus 1, x to the n plus r.
Can I make the series starts from negative infinity?
You could do that. That method would still work here. One of the reasons why I wanted to do this way, because I wanted to show you that the coefficient x to the r, what you'll always realize, it's always going to be your indicial equation. Right? The left side of your indicial equation should pop up here. So if you do think, this is an easy problem. Sometimes you'll take several lines to get it to a nice point. But if you realize that you're evaluating some terms and you don't get back the indicial equation, you made a mistake somewhere. You need to go back and check something. Right? So you might not see this if you just do that thing where you just assume it goes from negative to infinity. But if you start to shift indexes, this guy should pop out. The left side of your indicial equation will always be the coefficient of x to the r.
How did you get that part? The R
This guy here, I evaluated it when n equals 0. So I plug in n equals 0, n equals 0, n equals 0, n equals 0.
You don't have to do it for the other?
No, he's at 1. The point is I wanted the indexes to be the same. Right? So he starts at 0, he starts at 1. I needed him to catch up, so I validated at 0. And we got this term, and then I can start both series from 1. Based on what we did last time. So even if you didn't find the initial equation before, at this point you would know that here's where you can use this. Set this equal to 0 to find the initial equation. This gives an now equals minus an minus 1 over n equals r. That's our return solution. And so now we can just, after this is pretty much the same thing. There were some slight differences starting off, like you have to remember here that your indexes don't change. Basically, in the cases where we have singular points, we have to assume n plus r is the power, not just n. When we differentiate, the powers don't change. And if you evaluate some terms to try to get the indexes to be the same, your indicial equation should always show up with your as a coefficient of x to the r. So there are a lot of things here that have to connect. Yes?
Oh, when you found out the an, where did the first term go? Like, when the n was 0, where did that term go?
I plugged it in. This is the term when n equals 0.
Yeah, so, but then you found out the an, right?
Yeah.
Oh.
But remember what we did at this point. To get 0, we'd set all the coefficients equal to 0. Setting this equal to 0 would have just given me back the indicial equation. I already dealt with it. Right? So I can ignore it at this point and just go straight to this. Okay. So here, notice that your A0, first, now we want the solution for r equals, we already found both roots. We found 0 and 1. I only want the one for r equals 1. So this means I'm going to take this as my solution. R equals 1, this gives me n plus 1. Plug in r equals 1, this gives me n. Now what you're going to notice, you're going to start to find these guys. Notice that A0 is going to be 0, A1 A0 is itself. A1 is just going to be, when I plug in 1 here, minus A0 over 2. Minus A2 over 3 times 4. And so on. So this gives us y is equal to the series of a n x to the n plus r infinity. Sometimes I like to just factor this out. So it's x plus r times a0 minus a0 over 2. X minus, I want to write this as A0, A2, I didn't find it. A2 is when I put in 2 here, I get A1 here, and I get 2 times 3. Which is equal to A1 is minus A2 over 2. So it's A0 over 3 times 4. And so the x squared term would be A0 over 12 x squared. I'm just going to do the first few terms because I have a bigger example I want to get to. So A0 x squared. So basically that's the solution. And if I did it, I could do the same thing again for r equals 0. I can plug in r equals 0 here, and I get the other solution. All right, so you can think of this as the y1 and the other one as the y2. So just a little bit more nuanced, but basically it's the same as a series solution. Here's an example I really wanted to get to. It's actually from a past final, so I think it's good practice. because they ask you a lot of stuff here. They ask for the recursion formula, the coefficient associated. And they ask you to talk about the singular points. So this is a very typical thing to ask of you in this section. So it's, if you see this problem, it's going to be a really long one in general. So this is from spring 11, problem 9. We're given 3xy plus 2y prime plus x plus 5y 0. Show that x equals 0 is a regular singular point. We did that last time, how to show something was a regular singular point. We just take a couple limits, find the recursion formula. Or the coefficients. Of the series solution. Centered at x naught 0. Associated with the, they usually ask for the larger root, but they don't have to. Compute A1 and A2 if you're given that A0 equals 1. So if you read the instructions carefully here, they never actually asked us to give them the series solution, right? They asked us to show it's a regular singular point, find the recurrence formula, and only find A1 and A2. Sometimes they'll ask for the full solution, sometimes they won't. Make sure you read the problem carefully. Especially if they ask you for a lot of stuff, like here they're talking about singular points and then recurrence formula. They might not ask you for the whole solution, but read carefully to be sure. Of course, if you did all this, you would be able to find the solution anyway. But okay, how do you begin?
Limit.
Show x equals 0 is regular singular points. Okay, how do we do that?
Limit as x goes to 0.
Limit as x approaches 0 of what?
X
X.
times 2 over 3x.
Okay, so first thing you do is put it in standard form, right? So your y prime plus 2 over 3xy prime plus x plus 5 over 3xy equals 0, right? Now you're going to want to take x times this guy and find the limit as you approach the singular point. 2 over 3x. Here your x's cancel, we get 2/3, it's finite. You also find, you take x squared times this guy. So you have x plus 5 over 3x. So this cancels into that. And the answer is 0, which is also finite. Therefore, x equals 0 is a regular singular point. Okay, done. What's the next mission? Find the recursion point. Which means you're going to pretty much take it just before the last step of solving for the series solution. So what do we do here?
Times it by x.
Times it by x. To get a nice form so we can identify what the indicial equation is. So what is the indicial equation here?
3r plus 4 minus 1 plus 2r.
Equals 0.
That's it. So this is 3r squared. This will be minus 3r plus 2r. This means I have r times 3r minus 1 equals 0. So I have two solutions, r equals 0 or r equals 1/3. So 1/3 is our larger root, which means when I get to that indicial equation, the recurrence formula, I'm going to plug in r equals 1/3. But before that, just leave it as r, just to make things easier to write down. So assume y equals n equals 0 to infinity a n x to the n plus r. Again, let me reiterate here. They usually tell you when you have to find an indicial equation and all things like that, but let's pretend they didn't tell you. How do you know the difference between when you approach a series problem like this or like the way we were doing before, right? When do you know you have to assume n plus r and worry about an indicial equation, or just assume y equals x to the n and just do it as we were doing before? The main thing is when we have a singular point, right? If they're telling you that you want to find a series solution centered at a point that you know is a singular point because that point makes the first guy 0, you have to make that assumption, n plus r, right? Otherwise, just treat it as we did the old series solution, right? That's something important that you should probably write down. Even though they usually mention it, but just in case they don't, you should be able to recognize it. They're like, expand around this point. Oh, that's a singular point. Means you have to figure out first, is it regular? Can I even find a series solution? So you'd have to check that. Second, you'd have to make this sort of assumption. You'd have to shift the power a little bit because it won't work otherwise. Right? So plug this into the ODE. In this case, we shall obtain 3 times the series of n plus r, n plus r minus 1, n plus r, plus 2x times the series n plus r, n x to the n plus r, this from 0 to infinity. Open space. X squared times the y. So from 0 to infinity of a n x to the n plus r plus 2. And then 5x times the y. So we have this guy. First two are okay. This one I have to shift the power, set n to n minus 2, which means this guy's going to start from 2. n minus 2, x to the n plus r, plus 5. Shifts the guy to n minus 1. So he starts at 1, n minus 1, x to the n plus r. 0. He's at 2, which means everyone else has to catch up to him. You don't have to do this, but it would be nice to see if this guy pops out. So I'm just going to do it anyway. You could also do it, pretend everyone goes from negative infinity to infinity. You don't have to worry about it. But I always like to double check that I'm actually, this expansion is correct, and I can do that by evaluating some terms. So I'll evaluate the first 2 terms here. So I'm going to plug in n equals 0. and then plug in n equals 1. Here plug in n equals 0. Plug in n equals 1. This is going to not do anything. This guy I'm going to plug in n equals 1. Plus it's going to be the series of this whole jumbled mess here, starting from 2. Okay. Now let's look at this first part of it. Let's group the terms. I'm going to group all the a0 x to the r terms. Right? And what am I going to get? I'm going to get 3 r minus 1 plus 2r a0 x to the r plus, now group all these guys. I'm going to get 3 times 1 plus r times r a1 plus 2 times 1 plus r a1 equals 1 plus r. One more. Plus 5. A1. 2 1 plus r. 1 plus 5 plus 1 plus r plus the series. And now what do you notice? Here,
The R terms are minus 1.
it's the same guy here. So algebraically, I think we're good, right? Didn't mess up with a sign or anything like that. You can always double check. So that's why this is sort of nice. See, Nettie snickered just now.
So what if
got the
I
question correctly?
what if I just check the first term then go back to negative?
You could.
Just
Right.
check-
What you really want to check is the x to the r term. Right? If you evaluate correctly, the x to the r term should give you back this guy. But the thing is, you can find them ahead of time using just ignoring the parts that mess up. Okay, so now what we have, so we know basically after doing this, the series here is just going to be a combination of all the series here. So that's going to give us the recurrence relation. And they only asked us to find A1 and A2. We don't need to go find a bunch of terms. So, this is the recurrence relation. Yes?
What about the term with x to the 1 plus r?
This was here.
Yes.
You could set this equal to 0. What that would help you is to find, if you assume you know A0, you can actually find A1 in this equation. Right?
And it gives us the a0, so can you do that?
You can do that, yes. So just as the same, you set all coefficients to 0. The coefficient of the x to the r term will give you back the left side of your initial equation. Anyone else you set to 0 should be able to help you find the other a's. Right? So that's what the purpose of those guys are. But here, just trying to give them what they asked for, so I'm just trying to get to the recurrence relation really quick. So it's going to be, I'm going to solve for a n. It's going to be a bunch of stuff over 3 n plus r, n plus r minus 1. Okay, it's going to be minus 2 n plus r a n. Oh, this is,
That's A to the N.
it's also an a n. So I'm going to group the a n's. I'm going to want to factor out an a n from both of these here. So the denominator,
3 times N plus R. N plus R minus 1. Times plus 2.
plus 2
Times N plus R.
times n plus r.
That's it.
Okay, and so that takes care of the first two. This guy I'm going to move over. It's going to be minus an minus 2. And I'm going to move the other guy over. It's minus 5 an minus 1. So if r equals 1/3, what they're asking us for is this recurrence relation. Times n plus 1/3 times n plus r and n plus 1/3 minus 1 because we minus 2/3 plus 2 times n plus 1/3. I leave it with that. I mean, you could simplify it to get rid of complex fractions, but I wouldn't worry about it. So that was the recurrence relation. They also asked us to find A1 and A2. To find A1, I have a couple of options. I can either use this equation, or I can just continue by using the recurrence relation. Let's use this equation here, just to show you that this is actually useful for something. Okay, so we would have 3 times 1 plus 1/3 times 1/3 A1 plus 2 times 1 plus 1/3 A1 plus 5A0 equals 0. This means that A1 is equal to minus 5A0 all over 3 times 1 plus 1/3 times 1/3 plus 2 times 1 plus 1/3. And you should notice that this will coincide with this. And so equals minus 5 over After doing all this, I won't do it if you don't simplify.
Take off 5
Yeah.
points if you don't.
Yeah, we're like, oh, it's complex fraction.
I don't like it.
Deduct 5. Yeah. You go
The
through that. I
old
really
gritty
don't care.
tenure professors.
I mean, if you can get through this without a hitch, I'm going to assume you can simplify this.
The old gritty professors like, no.
Right. So
Simplify.
since A0 equals 1, right? Just plug in A0 equals 1. And they also asked us for A2, I believe. So A2, what I'm going to do is I'm going to use this, plug in n equals 2. So I'm going to get minus A0 minus 5A1 over 3 times 2 plus 1/3. And I'm plugging in n equals 2, so this is 4/3. Plus 2 times equals 2, that's 5/3, 7/3. A0 equals 1, then this gives us A2 would be minus 1 minus 5 times this guy. Yeah, so a lot of times finding the series solution here, you can see it's quite messy. So sometimes they don't even ask you for that. They just ask you for the first few terms.
Was this a problem you have to do, or you could choose out of the 5?
I remember.
Look it up.
Know how to
He
do
gave
it.
you the number.
Everyone in my class has to know how to do everything.
It was 11, so.
It was 9.
It was 9 of, so it must be a problem.
No, everyone has to know how to do it.
Damn.
Okay.
He's like, no.
Plus 25.
So in the last few minutes, but yeah, that covers everything we need for the test, which is next Monday. Do the homework. You can probably ask me some questions on Wednesday if we have time. So I just want to move on to 6.1. We're not going to do anything major. I just sort of want to derive a formula that they just tell you and you don't really know where it comes from.
It just came out of thin air.
Like, this is the Laplace Transform. Okay, so the definition.
Oh, the Laplace.
Laplace. It's Euler and Laplace.
Transformation.
It could be Laplace transformation or Laplace transforms. An integral transformation. The function t is a relation form. So, this is called an integral transformation. Now, transformations, if you want to think about them, they're more like generalized functions. So basically, remember what functions did was they take elements from one set and they assign to them elements in another set. If you think of a function that deals with functions, like it takes from a set of functions and gives you outputs from a set of other functions, we call that a transformation. One particular kind of transformation is an integral transformation, which it defines a function this way. For example, integration by substitution is an integral transformation, regular integration is an integral transformation, and basically it takes you one function as input, it outputs some other function. In the most general form, it actually even changes the variable, which is why you like substitution. Right? You say integral of f of x, the substitution transformation will give you some other function in terms of u. Why do we need to do this? Well, it makes it easier to solve the problem, right? So in general, these guys are very useful because they help us solve complicated problems by bringing us to a different environment that is easier to deal with. So one particular integral transformation is called the Laplace Transform. And it is super useful. Engineers love this, actually. So a lot of your engineering classes later on.
Love
are
is
gonna
a
be using
strong
Laplace
word.
It's a
transform.
Love is a
love-hate
strong
relationship.
word.
they are frequently observed in their natural habitat using this. Okay.
So what
It's
species
a very
is this?
important transform. The idea is to find the continuous analog of the power series. Right? So basically, you remember what the power series. It's sort of like this guy, a n x to the n. The thing is, this guy is a discrete function. Discrete means it only works on some values. So it's like, okay, n equals 0, n equals 1, n equals 2. Basically, you want to generalize the power series because we're realizing Calc 3, hey, these guys are sort of useful. We can use them to solve all sorts of problems. Let's make them even bigger and badder. Let's make sure they don't only work on integers, but they can work on all numbers, any number I want to pick. What about at pi, right? So you try to make this guy continuous, and so continuous. So basically, you want it to work not just from n equals 0 counting up to infinity, you want it to work on all t from 0 to infinity, everywhere, right? So here is what we're going to end up with being the Laplace transform. So basically, we're going to sort of show you where the idea for it comes from. So basically, we start with, I'm going to write this in a more suggestive way. F of t x to the t, right? I'm pretty much just replacing an by a function because I know it represents a function, and x to the n, I'm just using t instead of n's, right? But I'm going to want to make the t a continuous variable where the n was a discrete variable, right? To make continuous, okay, so the summation gives us discrete sums. What's the thing we know that gives us continuous sums? That's right, the integral.
He always does that. You guys are stupid. I just told you right there. You guys are stupid.
Right, that's we had a Riemann sum and we made it into...
No, doesn't ring a bell.
Okay, all right, so back in Calc 1 we learned if we wanted to make a summation continuous, we can find the area under a curve where we don't have to just count it integers and find the area of rectangles, we can literally find the area on any random interval because we transformed it into an integral. So the first order of business is to get something like this. That sort of now transforms this guy into something that works everywhere, right? Not just on integers. But it's not an efficient form. Why? Integrating something times x to the t is hard to integrate by itself normally. Mathematicians don't particularly like it. Engineers like it even less. If we're going to have an exponential, it turns out the best exponential to use is which one? What's the exponential we all like? E to the x. So we need to write this as e to the x. So that's the next thing they do. So then they're like, okay, take this. How do I write this where it looks something like e to the x?
E to the ln.
Right, e to the ln of that thing, right? So this gives us 0 to infinity of f of t, e to the t ln x dt. Now, we require two things. Well, one thing, but sort of in two parts. We assume x will have this form. Why? Because we want, this is an improper integral. We want it to converge. To sort of give us the best chance of converging, I don't want x to be bigger than 1. Because if I start taking powers of something that's bigger than 1, powers are getting bigger, this guy is going to diverge to infinity, which means my f of t would have to be really killing it to actually make this converge, right? So if I let my x be within 0 to 1, then this guy will get smaller and smaller, and so there's a better chance of converging. I don't want it to be between -1 and 0, because then I would get complex numbers, and I sort of want to stay away from those. Because if this is, say, a negative number, and my t happens to be a half, that gives me I, right? So we want to keep these in the real numbers set, and we also want to make sure this guy sort of converges. So we're going to put that restriction, which gives us something else. This makes ln x to be negative, right? So if s is a positive number, where s is a real number, we set ln x equals minus s. So I'm going to change the variable here, right? Because having the ln x here looks messy. So I replace ln x with another variable. I define this variable to be positive, so that I know that ln x is negative because my x is between 0 and 1. So this gives me 0 to infinity t e to the minus st dt. Now, since this is a definite integral, t the result will be a function of what? I'm going to integrate this dt, right? Then I'm going to plug in the limits, which means what? T's are going to disappear. But I have another variable here, s, which means my answer is going to have what? It's going to have s's in it, if it actually gives me something that converges and is non-zero. So this will be a function of s. So finally, we get, call this big F of s, so we're changing the function. Integral from 0 to infinity of f of t e to the minus st dt. And this, boys and girls, is called the Laplace Transform of the function f of t. Basically, here's what a power series would look like if it were continuous. It would be a Laplace transform.
It's French, right?
Yeah, I believe so. So, other notations. There are common notations here. So if I have f of s, it can be written with this fancy L for Laplace of f of t. And you can put this bracket s to emphasize it's a function of s. A lot of times people just leave that off because s is assumed to, it's the usual variable that we use, so sometimes just leave it off. Sometimes people, including myself, just get lazy and just write L of f of t or L of f, which sometimes I'll be right. So if you see any of these, they all mean the same thing. Be aware of that. But yeah, so your book sort of just said, okay, integral transforms are really useful. Here's a Laplace transform. We never really mentioned where it came from. This is sort of where it came from. This was the idea. And it turns out it's very useful in particular in solving differential equations. And we're going to use it to solve linear differential equations with constant coefficients, but you can make it more general. But that we will do next time. Okay. So make sure you do the homework for up to 5.5, so that will prepare you for the test. The review problems for the test, for the next 2 tests, are already up on the website, so be sure to check that out.